Okay, I'm just going to do only the introduction to memory part. Okay, so what I'm showing you here, right, is basically the memory itself. Memory arrays are classified into many different kinds of memories. You have random access memory, serial access memory, and content addressable memory. Okay, random access memory is, for example, data that you can randomly access. You give an address, you will get data. Okay, and that can be classified further into volatile and non-volatile. Okay, volatile is what we call RAM, DRAM, right? When we say the RAM sitting in your computer, we mean it's a random access memory. One, it will allow you to access memory randomly. Given an address, any address, get the data. On the other hand, it is volatile. That means when if power is turned off, everything is gone. Okay, therefore, it is not possible for you to just switch on the computer and work only with RAMs. No, you need a non-volatile memory to start off your program and stuff, and that's why you have ROMs, which are called read-only memories or non-volatile memories, right? Further, volatile memory is classified as static random access memory and dynamic random access memory. These two are very different. Non-volatile memory again is, programmable ROM, erasable ROM, right? So there are electrically erasable programmable ROMs, flash memory, a lot of these kind of things, right? Likewise, you have serial access memory, shift register, queues, first in queues are first in first out, right? Or last in first out. You have stacks, right? Serial in, parallel out, these are just registers. We have seen these in the digital systems course, parallel in, serial out, and so on. Okay, so in order for the processor to actually deal with memory in an efficient manner, ideally we would have liked like a memory store which is infinitely fast and infinitely large, right? So basically the idea is the cycles per instruction is the number of, we have seen this number of processor clock cycles required per instruction. Remember, we are saying processor clock cycle because the processor's clock period can be different from that of the memory. Okay, and ideally we are saying that if you had infinite cache memory and infinitely fast memory, okay, then I would get a certain CPI, right? That is the fastest that my processor could work at. However, in reality, obviously your speed is going to be limited, and therefore you are going to make your processor, we are going to assume, is infinite size but finite speed, and therefore you are now going to add to this CPI, ideal CPI that you got, a finite cache penalty, FCP, out here, right? And of course, when you make your size also finite, it's going to be worse than that. Okay, so the idea is, first of all, when you are fetching data from the memory, if you fetch something now, you will access it's likely you will need it soon. Okay, and therefore you are going to use this temporal locality idea to design, to optimize your memory. Likewise, spatial locality. If you access something now, you will also need what is just around it, typically an array, right? If you access x of 1, you might, very likely you are going to access x of 2 and x of 3 soon after this, right? So therefore you are going to exploit this to divide memory itself into a hierarchy. Okay, and therefore the processor which has register file is the fastest memory that it can access, but obviously is very small, limited inside the processor. Then you have something called an L1 cache, okay, which is basically very fast but small. Okay, however, it is still slower than your register file. Okay, so idea is, when you miss in the register, you got to go to your L1 cache, right? And if you get that data in your L1 cache, well and good, it's a least penalty you had compared to your register file. Then you make an other cache called a level 2 cache, L2 cache, which is slower but bigger. Okay, so that's the idea. So again, if you miss in L1, you go to L2 and so on, right? So basically the whole idea is that if you do miss data in your register, right, it can be a serious problem, and therefore you have to go to L2 cache, then L3 cache. So every penalty is going to basically add to your cycles per instruction, right. So that is what is actually shown here. So the finite cache penalty is basically delay divided by the divided by something that relates to the number of hits in the L2, right. Likewise, there is a finite cache penalty that you are going to see for L3 and L4, okay. So that's the key idea here, and therefore you can even quantify the finite cache penalty as I am showing you here. But anyway, I am not going to focus on that in this particular course, okay. So this is a sort of a very good slide for us to conclude our discussion in the computer organization course. So there's a processor, there's a register, and then there is an on-chip cache, okay. Then there is a second level cache, then there's a main memory which is DRAM. Then there is a secondary storage which is disk, and the tertiary storage which is tape, okay. So the speed of access is going to be very, very important here, and this depends on the size also, okay. So because registers are very small, right, if you look at it, registers and SRAM memory L1 cache are very similar in their transistor structure, right. However, because the registers are small, it's going to be much faster to access compared to your thing, okay. So typically 1 nanosecond access, right, SRAM memory will be of the order of bytes. You go to kilobytes, second level, it can become 10 nanoseconds access, right. See, because accessing the last memory location, there is a wire delay that you have to worry about, right. Then you go to main memory, which is DRAM. So what gets plugged into your computer's PCI slot is the DRAM, okay. And then that is about 100 nanoseconds. This is a slightly dated slide or outdated slide, but even today we are able to bring that down to 30 nanoseconds, okay, instead of 100. So what is important to note is the order of magnitude jump. 1 is becoming 10, 10 is becoming 100, then 100 nanoseconds is becoming 10 milliseconds, and then terabytes of storage on disk or tape is 10 seconds, okay. So basically there is severe orders of magnitude increase when you go from one level of memory to another, and that is going to affect your performance ultimately. It does not matter how fast you make the processor, unless you make the processor and memory talk to each other efficiently, you are not going to get away with good performance at the processor, okay. And therefore it is extremely important to have a very good cache hierarchy like this, first of all, and two, your caching algorithms have to be very, very efficient. If you get the wrong data and put it in L1 cache, there is no use, okay. And likewise, the size of the cache memory is also important. Additionally, if you remember the initial processor picture I showed you, right, the L1, L2, L3, all these caches were actually sitting inside the processor, okay. L3 was shared across the cores, L2 was shared inside, each processor had its own L1 memory, right. So the idea is not just make your processor faster, but also pull in lot of this memory into the microprocessor itself, into the microprocessor chip, right. Once you go out of the chip, you have to communicate on the board, and therefore that communication is going to take much longer. So therefore you pull as much memory as you can, L1, L2, L3, into the chip itself and make it much faster, and with all of this your performance of the processor can go up significantly. So thank you for watching these lectures on computer organization.